Welcome everyone. In this video, I want to go over problem number 5, section 7.4. And I did each part in detail, and that's going to help you kind of do the other proofs also. So let's see what the problem says. So for warm-up, it says can compute the adjunct matrices of the following elementary matrices, which of the adjoint is also an elementary matrix. Again, adjunct or adjoint is the same thing, and I will call it adjoint for this exercise. Now, these are elementary matrices. Don't forget, an elementary matrix you obtain by it's one row operation away from the identity matrix. For example, if you take I2 and multiply row 2 by -5, you get that matrix. So this is an elementary matrix. If you take I2 and interchange row 1 and row 2, you get that matrix. If you take I3 and multiply row 2 by 4, you get that matrix. And if you take R3 and interchange row 3 and row 1, you get that matrix. And if you take R3 multiply row 3 by -3 and add it to R1, then you get this matrix. So all three types of operations are here done to I here, and you get all these elementary matrices. Now, finding the adjunct, let's go over that. So I did some of them slowly to kind of show you how it works. So now, first of all, know that C, I called that the matrix of the cofactors. And the cofactor is for each entry is given by this formula. Cij is -1 to the power of I plus j times Mij. Please check my lecture on determinants and you'll see where that comes from. So if you want to find the matrix of the cofactors for this one, so C11 is just going to be -1 to the power of 1 plus 1 times the determinant of that matrix. And that's a 1 by 1 matrix, and the determinant, well, we here. The determinant of a 1 by 1 matrix is just the entry itself, so it's right here. Now, if you want to find C22 is -1 to the power of, actually this is C12, plus -1 to the power of 1 plus 2 and times the determinant of this matrix, which is just 0. If you want to find that is C21, so -1 to the power of 2 plus 1 and times the determinant of that matrix, which is one entry, so it's just 0. And finally, for this one is C22, so -1 to the power of 4, which is just 1, and times that number, because it's the determinant of just a 1 by 1 matrix, and it's 1. Plus the adjunct of these, the transpose of the matrix of the cofactors, which in this case, it's the same thing. So if you start with I and multiply row 1 by -5, you are going to get that matrix. Therefore, that's an elementary matrix. Now for next one is interchanging row 1 and row 2. Apply that to I2 and you get this matrix. And again, the matrix of the cofactors, if you do it the same way, you're going to get 0, -1, -1, 0, and the adjoint of A is the transpose of the matrix of the cofactors, which is going to give you the same answer. If you take I and interchange R1 and 2, you get that, and that's the operation is done. So you can't multiply that by -2, because that's going to be, that's not an operation anyway. So you cannot get that matrix by doing just one row operation to the identity matrix, or I2 in this case. Therefore, adjoint of is not an elementary matrix. So please pay attention to those details. Next one, if you take I3, multiply the row 2 of I3 by 4, then you get this matrix. And the matrix of the cofactors, you can use this for each entry, and I wrote it for you for this problem. So for the first entry is going to be the minor is the determinant of that matrix, and I put it here, and this is negative because of that formula. So for the second one is going to be the determinant of this matrix. So you put it here. Third one is going to be the determinant of that one, and so on. So I'm sure you're familiar with that. If you calculate, you get that matrix, and the transpose of that matrix is the same matrix itself. So that's adjoint of E. You cannot get this matrix by doing just one operation to I, and this is not an elementary matrix. So when we had a 2 by 2 matrix, we got an elementary matrix when we did this row operation, but not for 3 by 3. Next matrix, if you take I3, interchange row 1 and row 3, you get this matrix, and I called it A in this case. It could be E, it doesn't make a difference. And I did calculate the joint of A. I use technology, that's what you get, and this is not an elementary matrix. So basically, what happens, you just get that matrix and multiply it by -1, and you get that, and you cannot get that matrix by performing one row operation to I. So it won't happen, so not elementary. And this one, if you take I3 and you do -3R3 plus R2, you get that matrix, the adjoint of that matrix, you get this, and I use technology for this one. And this is, if you take I3 and you do 3R3 plus R1, and you get the same matrix. So I did performed one operation to I3, and I got this matrix. Therefore, the adjoint of A or E in this case is an elementary matrix. Now it says part B and C, we're going to do this together. I said B and C at the same time. If N equals to 2 and E is type 1, so for our test book is multiply row I by IN by a non-zero number C and obtain E, then adjugate is also an elementary matrix. Kind of saw that. But the general form, what you can say, if you say I2 is that, and I say I2, that means that's 2 by 2. So if you do CR1, we get this matrix. And if you find the matrix of the cofactors for this matrix, you can use these formulas. Again, C11 is -1 to the power of 1 plus 1 times 1. I'm sure you already know that. So you get 1, C12 is going to give you 0, C21 is going to give you 0, and C22 is going to give you C. So C becomes 1, 0, 0, C, and you can obtain this by multiplying I2, row 2 of I2 by the constant. So again, this C and this C, they're not the same. This is just a constant. And the adjugate of D is the transpose of that matrix, and it's the same thing, and it is elementary. Now, if you take I2 and multiply row 2 by a constant, you get this matrix. And same way, if you perform the cofactors, so you get C11 is going to be C, C21 is going to be 0, C12 is going to be 0, and C22 is going to be 1. So you get that matrix. And the adjoint of E2 is the transpose of that matrix. This is matrix of the cofactors, which is the same thing. And obviously, you see this is an elementary matrix. Adjoint of E1 and adjoint of E2 are elementary because the minor Mij for a 2 by 2 matrix is the determinant of a 1 by 1 matrix, which is the entry of that matrix, and I showed it to you. So that's why when it's 2 by 2, you do get an elementary matrix when you multiply a row by a constant. If n is greater than 2, let's see what happens. I started with the identity matrix. I took a row K and multiplied that by C. So that's what we get. So this is our that EI, and then the entry K by kth entry became C, and this is an n by n matrix. Now, if you want to calculate the matrix of the cofactors, again, this is the matrix of the cofactors. So Cij for each entry, well, that's the formula for the Cij. Cij equals to 0, so it's going to be 0 if I is not equal to 0. So we kind of saw that. So it's going to be 0 for when I is not equal to j. If I equals to j for the diagonal, what happens? Cii or Cjj equals to C. So, and actually this is, call this CKK is much safer. So whenever it's not K, if I take this cofactor is going to be the determinant. Well, the sign, you know how what happens of that, and these are all ones, except this is C. So if you calculate that, you get C. But if you take this cofactor, CKK, and you calculate it, then you get 1 because the determinant of the minor is going to be 1 in this case. So now if you substitute, so what happens, the matrix of the cofactors becomes all C's except that it's 1, and the transpose is the same thing as that. And this is not an elementary matrix because you cannot take I and perform one of the permitted row operations and get C's everywhere except 1 and 3 to be 1. So not elementary, that's the general form. Now, next point, I used a different approach. So show that if E is type 2 means exchange rows of In to obtain E, then a joint of E is never elementary matrix. Now, there's some notes I put here for you. I want you to go over. This is from the last lecture. So if you, first of all, know, if you have a matrix and you permute 2 rows, that's just interchanging 2 rows. That's how I show it. Permute 2 rows and you get a matrix B, then the determinant of B is the same as negative the determinant of A. So the sign of the determinant changes. Remember this note, all of them actually. So if you have I and you permute 2 rows to I generally, it could be IN, then you get E. The determinant of E is minus the determinant of I, but the determinant of I, we know it's 1, so it's going to be negative 1. Note number 3, if you have I and you permute 2 rows and you get E, the inverse of that matrix is also an elementary matrix, and it's the same type. And I showed it here with an example, just for you to understand. If I have I3 and I interchange row 1 and row 3, so I get that. If I want to find the inverse of that matrix, so you can just find it by putting the matrix here and I here. And if you do P1, 3 or interchange row 1 and row 3, this becomes I and that becomes the inverse. And guess what? The inverse is the same thing, same matrix as E. So not to forget that. If I take any of those matrices, E or inverse, they're the same, I multiply by -1, I get this matrix, and this matrix is not elementary. Why did I do all that? Because if you go to the proof, we know that A times the joint of A is the determinant of A times I. Please watch my last lecture on application of determinants. So we can say for elementary matrices, E times the joint of E is determinant of E times I. But what is the determinant of E? That's -1. So E times the joint of E is -1 times I. And if I multiply both sides by E inverse, so what happens, E inverse times E is just I, I times the joint of E is just a joint of E, and this side we get -1 times. You don't have to write that I, so it's -1 times E inverse, or -1 times E, or -E. This is not an elementary matrix. So E was obtained by permuting rho I and rho J. Therefore, -E is not elementary. So that's a fast way of proving this. You can do the same thing for part E. Part E says show if E is type 3, add a multiple of rho I of In to rho J to obtain E. Then the joint of E is not an elementary matrix, is an elementary matrix of type 3. So we start with I. We do alpha times Ri plus Rj is going to give you change Rj, and you get that elementary matrix. The determinant of I in that case equals to, when this operation doesn't change the value of the determinant. So it's going to be the determinant of I is the determinant of E, and that's 1. E times the joint of E is the determinant of E times I. So then you can say E times the joint of E, the determinant of E in this case is 1. So it's just I. So E times the joint of E is I, therefore the joint of E is just E inverse. And we know the inverse of an elementary matrix is also an elementary matrix. So I think that's it for this problem. Please watch it a couple of times, and I will help you for the other proofs too. I will upload some more proofs. So thank you for watching. Have a great one, everyone.